Hello everyone, welcome to today's webinar. I'm Madhu Govindarajan from the MathWorks. I'm going to show you how I built a smart robot using Simulink and Arduino. Here's a look at the agenda. First, I will introduce the hardware that was used and the specific purpose of this robot. Then I will show how Simulink and Stateflow helped me build this robot, and I'll finish up with key takeaways. So I built the hardware into this specific configuration and used an Arduino Mega as the brain for this robot. The IR sensor acts as the eye for this robot. This robot's purpose was to carry the Rubik's Cube and move in a straight line while avoiding other robots. We did not want the robot to drop the load. The way I wanted this robot to interact with obstacles like wall, my colleagues, or other robots is as follows. Avoid stationary obstacles by coming to a complete stop and wait for the person or the robot to move away. And if the obstacle is moving, then I want my robot to try and match the speed of the moving target. Here is a video of the robot in action. It is following a Lego EV3 robot which I controlled using Simulink. I tested the robot in different conditions to see if the robot drops the Rubik's Cube while trying to avoid the EV3 robot. It was successful in all the test cases. Now that we have seen the purpose of this robot, let us see how Simulink and Stateflow helped me here. Before I go to Simulink and show the demo, I'm going to show you the steps involved. The first step was to simulate the barebone kinematics and understand the behavior of this robot in simulation environment. The next step was to validate the model by comparing actual robot results with the simulation results. The next step was to program the logic in simulation world and then deploy the code onto the hardware to validate it. I'll be using this slide throughout the product demonstration so that we know exactly which step each portion of the demo corresponds to. So let us see how I did the simulation of this robot in Simulink. Going in, I knew that this is a differential drive robot, which means that you can control the turn of this robot by varying speeds on two sides of the robot. So let us consider this two-dimensional space x and y. We can use the kinematic equations of any differential drive robot. The robot position at every instant in time can be described using these equations. Here theta is the angular position of the robot, and we can see that all of these can be calculated using the wheel velocities. Now let us go to Simulink and see how I did the first step of barebone modeling. This is a simulation-only model which I used to simulate the kinematic equations that we just saw in the slides. For those who are not familiar with Simulink, it is a graphical programming environment, and Simulink library consists of blocks that you can connect using arrows. The flow of a Simulink model is usually from left to right. Here I'm using the signal builder block to define the input commands to the wheels. Then I'm using the multiport switch block to toggle between the different input commands. The first set of commands will make the robot turn left, the second will make it go straight, and the third will make it turn right. These set of commands are then sent to this simulation subsystem. A subsystem is a collection of blocks that is usually formed to achieve a specific purpose. In this case, it is going to simulate the kinematic equations. This subsystem will simulate the encoder values and send it to the next subsystem. Here I'm using the basic blocks from Simulink to implement the equation for angular velocity. So if we read this, it is VR minus VL divided by L. And I'm then converting it to degrees per second using this multiplication factor. In the next subsystem, I'm implementing the equations to calculate the position of this robot. I'm incorporating a previously written function from MATLAB using this MATLAB function block. This block allows you to bring a chunk of code from MATLAB into Simulink as long as the function has inputs and outputs. After calculating the position of the robot using these equations, I'm passing them to the XY graph to get a visual representation of the moving robot. I'm using the simulation paste block from Simulink library to make the simulations look almost real time. That is why this model takes about 10 seconds every time I run the simulation. We can see from this figure that the robot will make a left turn that looks like this in under 10 seconds when I feed the first set of commands to the wheels as the input. The third set of commands will make the robot turn right, much similar to the first set of commands, as I'm feeding the opposite inputs to both the wheels of this robot. The other set of commands will make the robot move in a straight line. Using this approach, you can test your model in Simulink and understand the behavior of your systems using simulations. It was particularly helpful for me to know how far the robot would go under different test scenarios. Now let us go back to the slides to see our next step. It's always a good practice to validate your models, as your simulations are only as good as your mathematical models. So in this model, I've changed some blocks and configured this model so that we can generate code and download it automatically to the hardware, all with the click of a button. The left side is exactly the same as the previous simulation model that we just saw. I'm doing this so that we can compare the actual results to the simulation results. I've replaced the simulation subsystem with this one, which contains the motor actuator blocks that are a part of the Simulink support package for Arduino. Once you have created a model and configured it properly, to generate code and download it to Arduino, all you have to do is click on Deploy to Hardware button. Using this technique, I've already deployed the code to the robot. The code deployed will make the robot turn left, and to show this in action, I'm using a webcam here. The markings on the floor help me read up to 150 centimeters in length and 50 centimeters in breadth. I'm also using a ruler to measure how far it goes beyond the 150 centimeters mark. The simulation and the actual results matched very closely. In the interest of time, I'm going to show a video of the other two sets of command in action that will make the robot go straight and to the right. In any Simulink model, you can show the data value of a signal by right-clicking on it and selecting this option. We can see from the Simulink model that the distance moved in Y must be 126 centimeters for the straight line. And for the next set of commands, the distance moved is supposed to be 167 centimeters. This way, you can validate any simulation model by testing the code out on the actual hardware using the automatic code generation feature. Now that we have seen how to perform kinematic model simulations and test them on the actual hardware, let me show you the next step in this project. Now we'll talk about how I programmed the logic behind this robot. The requirements that I showed in an earlier slide on how this robot should interact with obstacles are translated into these states. For instance, the condition that the robot must move forward at all times except when faced by an obstacle is cruise state. And the other two conditions are brake and follow leader respectively. Before going into Simulink, here are some observations that I've made about the robot. Any deceleration that was faster than a stopping time of 2 seconds made the robot drop the Rubik's Cube. The maximum speed of this robot is 30 centimeters per second. So to explain using this profile, let us say that I made the control commands to make the robot stop at 3 seconds. The Rubik's Cube fell off the robot in this case. And conditions where I sent commands that would make the robot stop at any time greater than 4 seconds ensured that the requirement of not dropping the Rubik's Cube was met. And that is why I'm going to use the slope of this deceleration profile in all my models to make sure that the robot does not drop the Rubik's Cube. In this Simulink model, I am using a Stateflow chart to implement the logic. Again, this is also a simulation-only model to test the logic under different test scenarios. The right side uses the same subsystem from the previous simulation model of the barebone kinematics. And here, I am going to take both the wheel commands and pass them through a block called unit delay. What this block does is that it will give me the input commands to the wheels from previous instant in time. I am taking this and the velocity values out of this subsystem using the goto block as I need them as part of my logic. I have named this chart Cruise Control and Automatic Braking as I'm taking some concepts from these techniques to implement the logic of this robot. The requirements that we saw in the presentation are copied here as comments inside the Simulink model. I have 3 states shown here in the chart. Before going into these to understand their contents, let us see how the transitions in between them will happen. It uses the IR sensor data, and if there is no obstacle in front of the robot, distance value greater than 50 centimeters, then the robot will be in cruise state. It transitions to the follow leader state whenever the distance value reduces below 50 centimeters and if it is greater than 15 centimeters. Any value below 15 centimeters will make the robot enter the brake state. Let us take a quick look at what these states do. The cruise state sends the same commands to both wheels, which will make the robot move at the maximum possible speed. We can see from here that this is the default state. What that means is the robot enters this state whenever it is started. It checks for the transition conditions connected to this state before executing the contents, and it moves away only when the transition condition is met. Let us see the contents of the follow leader state. It has 3 substates to be executed when the distance from the IR sensor is decreasing, increasing, and when it is constant. The default value is the junction where it compares the IR sensor measurement to the previous instant measurement. And based on this, it enters one of these 3 substates. If the distance is constant in the follow leader state, it means that the obstacle in front of my robot or the leader is also moving at the same speed as my robot, and all I have to do is maintain the speed at the same value. For this, I'm using the input commands from the previous instant that I showed before using the unit delay block. In the distance decreasing substate, there are 2 substates of this based on how fast the distance is decreasing. If an obstacle suddenly pops in front of a robot, let us say a colleague of mine was passing by, then the robot should enter the sharp decrease state where it will decelerate using the maximum slope value that we saw from the presentation. This could mean that the robot will run into the obstacle and collide with it. But the collision will be slow enough that the robot will not drop the Rubik's Cube. The other substate is gradual decrease, where for the first second, the robot is using the information on how fast the distance in front of it is changing and feeds a percentage change to the input commands. I chose this pattern because it will provide some time for the IR sensor noise to stabilize. Then it enters the decelerate substate, which is the same as the sharp decrease substate. The distance increasing substate does the same thing as the distance decreasing substate, except in the opposite direction. To test the logic and see how the robot performs in different scenarios, I've created 3 different velocity profiles for the robot ahead. Here, the values are in centimeters per second, so the first profile means that the robot ahead is driving at the same speed as our robot, and it drops its speed suddenly to 15 centimeters per second. In order to understand this better, let us imagine real-life scenarios. Think of these as cars ahead of us while we are driving. So the first profile will mimic a driver who just did a lane change and cut right in front of you, and this driver is at a slower pace, which is constant. He then performs a lane change away from the lane. The second one is a driver who did a lane change but is now accelerating in your lane with a constant acceleration. The third one is a driver who slows down over a period of time and then accelerates at a different rate and moves away. So let us test these three different scenarios to see how the robot does in following the leading robot ahead. We can see from the scope that when the robot ahead drops its speed significantly, our robot is slowing down at the maximum possible speed mentioned by the limitation that we talked about. The same condition holds true when it is increasing back again. Let us see what happens in the second test scenario. We can see here that the robot is compensating the sharp decrease the same way it did in the previous run. And during the gradual increase, we can see that the robot waits for 1 second before it accelerates quickly and repeats this process till the distance between them is constant again. Now that we have tested and confirmed that the robot works fine in all simulation test cases, I will show you how I used stateflow animations to visualize the logic. Our focus is on the follow leader substate and to see how the robot behaves while it makes the decisions. We can dig deep here and see how and when it executes the contents of the distance decreasing substate and the transitions as and when it happens between the slow fall and the decelerate substates here. Similarly, we can visualize the increasing substate and its transitions as the decisions are being made by the robot. I used this process to iteratively test and improve the logic. Using this trial and error approach, I landed at this 5% value that I have chosen for this substate because this gave me the desirable performance for the robot in real world. Now let us go back to the slides to see the last step in the robot building process. Now, as we did with the barebone kinematic model, we can generate code from the logic algorithms and run it on our robot. One key difference from the simulation model that I just showed you is that I will be reading data from an actual sensor, so I will have some noise to deal with. To address this, we will have to implement a low-pass filter. In hardware, you can use an RC circuit which will act as a low-pass filter. In software, to get a similar behavior, we can use transfer functions. Now I'll go to Simulink and show how I built a low-pass filter and tuned these parameters k and tau of this transfer function. This model takes the right-hand side from the previous hardware model, and I've added the logic that we just tested in the simulation world. Instead of the simulated IR sensor values, we can bring in measurements from the real world to Simulink. This is the signal that we are going to filter using transfer functions. I've added the default block from the Simulink library, which implements the k and tau value as parameters of the discrete transfer function. I'm going to start with the default values, but I'm not sure if those values are going to give me an appropriate cutoff frequency. And since I have to tune these parameters as the logic is running on the hardware, I'm going to use a special capability that Simulink offers called external mode. External mode allows you to monitor signals from Arduino, which we can use here to see how the filter is performing. And we can also use the same feature to tune parameters in the algorithm while code is running on the hardware. And remember, during this approach, the Arduino is tethered to the computer via an USB cable. Now when I click on the play button, Simulink is generating and downloading the code to the hardware. It provides status updates in the bottom bar. I've placed the robot on a raised platform in this case the Rubik's Cube itself, so that the wheels are free to spin and we can tune the filter. So the real world analog sensor data is brought into Simulink using this analog input block, and it is converted to millivolt. Then I'm filtering the signal using this discrete transfer function block, which is then converted to IR distance values using the lookup table. The lookup table has voltage versus distance graph that I extracted from the datasheet of the sensor. So let us take a look at the scope to see how the filter is performing. The default transfer function block that I used is merely replicating the signal, and it is adding an offset value. For this, I've created a MATLAB script where we can get different transfer functions for different cutoff frequencies based on the equations that we saw in the slide. It is using MATLAB's built-in functions to create the transfer function and then convert it to the discrete domain. I'm going to use 10 as the cutoff frequency for the first experiment. When I run the script, I can see the value for numerator and denominator that I should enter into the Simulink block. Now we can see from the scope that the filter is trying to match the incoming signal and the offset is gone. But we cannot understand much about the performance of the filter from this. So instead of looking at the raw analog voltages, let us look at the IR sensor measurements that are coming out of the lookup table. We can see that this is still very noisy and the values vary with a plus or minus of almost 10 centimeters from the mean value. Let us try other values for the cutoff frequency and see if we can reduce the filtered IR distance noise. So I'm going to use the value of 5 as the cutoff frequency and design the new filter. Now again, we have to use these values in the Simulink block. Notice here that the code is still running on the hardware as we are tuning the parameter to get better distance measurements. And the advantage here is that I don't have to recompile the code every time I need to try a new parameter. We can see from the scope that the noise value has reduced significantly. It is within plus or minus 5 centimeters. So this was the final model that I used on the robot, and I showed you the video of the robot in action following a EV3. This is how you can validate the logic of your robot on the real hardware. Here's another video of the robot encountering a human being. We can see here that the robot does not stop as long as the obstacle is moving, even though it is not a robot. Now let us see the key takeaways from this webinar. We saw how simulations can help develop algorithms which can then be deployed to the hardware using automatic code generation feature. This was helpful in understanding the behavior for this specific robot. We saw how Stateflow can help program your logic. I did not have to write any complicated nested loops or if loops because Stateflow combines graphical and textual representation of code. Stateflow also helped us visually validate the logic as Stateflow animations showed how the decision was taken during different test scenarios. We also saw how we can implement any logic in the hardware and modify parameters as the algorithms running on the hardware. We also saw that we did not have to recompile the code during this process. In the same example of IR sensor noise filtering, we saw how signal processing routines can be implemented using a simple block. The other feature about Simulink is that you can use the same approach to program other hardware as well. For example, I created an obstacle avoiding robot using EV3 that avoids these cones by going around them in a specific pattern. You can even program Raspberry Pi using these same techniques. And here is a robot that one of my colleagues created. What this robot does is that it detects green colors and starts tracking it. If you're interested in learning more about these robots, just do a quick search for the terms I've used on these slides anywhere on mathworks.com. you will land on the appropriate resources. With that, we have come to the end of this webinar. I would like to make a quick announcement to the attendees. If you have any project where you programmed your low-cost hardware using MATLAB or Simulink, here is a great challenge that is happening right now. All you have to do is take a video of your project in action and share it via YouTube. Then fill out a form on our website and you can win up to $1,000. The interesting aspect about this challenge to me was that community gets to vote on the video and help you win the challenge. If you're interested in learning more about this, please scan the QR code on the bottom right corner or search MATLAB and Simulink Hardware Challenge. Thanks for your attention and time. Hope you enjoyed the presentation.